Hello and welcome to your Solid Mechanics Virtual Lab. In today's session, we will cover experiment 4, named the deflection of a cantilever beam. Now, from our last experiment, we determined the modulus of elasticity for a simply supported beam. Now, the question is, what if the beam is a cantilever? And what is a cantilever anyway? Well, I'm glad you asked. A cantilever beam is shown on the screen, and it is characterized by two main things. It is a beam that has a fixed support on one end and a free support on the other end. Cantilevers are a really important part of the structures that we design and build. They are quintessential in a lot of our projects, and some of them we might not even realize. A cantilever can be as simple as the balcony in your house, to something as impressive as the skyline for a proposed project in Dubai, and we even have some cantilevers here in Kuwait. Can you spot the cantilever in our central bank building? It's actually right here. As you can see, cantilevers are pretty much everywhere in our structures, and it's important for us to understand how they behave when loads are being applied on them. So we're going to take a look at some of the behavior of cantilever beams. Now, a cantilever is characterized, as we mentioned before, with one end being fixed while the other can freely deflect. You can basically set up your cantilever in many different ways. You can model it using a point load. You can model it using a distributed load. You can consider the self-weight, and that's also going to be a distributed load. But pretty much the concept is the same. One end is going to be fixed, the other is going to be free, and because of these different end conditions, they're going to behave kind of differently than what we've seen before. As you can see, towards the end of the fixed support, there is little deflection, actually no deflection whatsoever, and no rotation. And as for the free end, you have the maximum amount of deflection being generated at that free end, and as you can see as well, the free end is being allowed to rotate from the neutral position of the beam. Now, let's consider this situation. Now, with this setup that we have on the screen as shown, we can determine the moment using the following equation. Sigma is going to equal my over I. If we plug in m, y, and I based on the variables that we have, the moment is basically going to be the force multiplied by the distance from the fixed support, so that's going to be PA. The distance to the neutral axis is going to be h over 2, and the moment of inertia for a rectangular cross-section is going to be bh cubed over 12. With a little rearranging, you get the equation 6pa over bh squared. Now, to calculate the deflection at that free end, we use the following equation. Again, using the same setup and the same cross-section as we saw on the previous slide, the maximum deflection is going to be pa squared over 6ei, all multiplied into 3l minus a. Now, again, the point of this experiment is to determine the experimental modulus of elasticity, so I'm going to swap out sigma and E, and we will use the equation shown at the bottom. Now, for today's experiment, we're going to try and determine the modulus of elasticity for a beam that is in a cantilever position in two different ways, and the increasing load method and the decreasing load method. The increasing load method is when we apply an initial load and then increment it until we get to the load that we want to apply. And then we're going to measure the decreasing load method, where we start off with the maximum amount of load and then start to eventually reduce it. As you can imagine, when we increase the load, the deflection is going to increase. When we decrease the load, the deflection is going to decrease. We're going to see if there's any difference between the two methods. Before we proceed, I need you to perform some calculations. Now, we have a beam that is going to have a total length of 800 millimeters and has a cross-section which is 20 by 6. So B is 20 and H is 6. Let's consider that the maximum moment that we want at the fixed end is going to be 100 megapascals. Suppose that we also want to apply a load at a distance of 500 from the fixed support. So from the beginning of the fixed support, 500 millimeters away, that's where the load is going to be applied. And at the end of the beam, at around 800 millimeters, that's where the maximum deflection is going to occur. Given all these, let's try and determine the maximum load that we can apply on the beam so that we don't exceed 100 megapascals at the fixed support. So sigma is 6 pa over bh squared, like we saw before. Substituting, 100 MPa is going to equal to everything except p. P is going to be our variable. If we solve for p, we're going to obtain p equals 24 newtons. So we're going to try and go lower than 24 newtons. So we're going to select 3 weights that are going to be smaller than this. Now from this, we can determine 3 loads that we can apply on the beam, just like I mentioned earlier. And then once we apply the loads, we can measure the deflection, we can plug them into the equation for the deflection, and then solve backwards for E. Now, for the worksheet that we need to solve, we need to measure the deflection of steel bars using experimental means using 2 different methods. We're going to look at the increasing and the decreasing load methods. Then, once we apply the loads and get the deflections, we're going to use them to calculate the experimental modulus of elasticity for each of the methods. Then, using the 2 averages, we're going to compare them to the actual modulus of elasticity for steel, which is 200 gigapascals. Now, I'm going to leave you with a demonstration, which is going to where I'm going to show you how this experiment is done, how the setup is going to be done. I'm going to use the exact same setup as the calculation slide from previous, as I've previously showed you. Make sure that you watch it and use the numbers that come up from the demonstration in your worksheets, which are also going to be on my LMS. On to the demonstration. So, what do I have here? I have a stainless steel rod. It measures 1,000 millimeters long and has a cross section that is 20 millimeters wide and 6 millimeters high. You might recall from the show that you watched earlier that we solved for a problem for a beam that is 800 millimeters long. Why on earth am I using a beam that is 1,000 millimeters long? Well, the answer is simple. If I were to place my beam that is, let's suppose that this is 800 mm long, you'll see that I really don't have much room here. So therefore, this is not really going to act as a fixed support. What I'm going to do instead is I'm going to take a much longer beam and cancel a part of it out. I've already put in a marker where the 800 mm line would be. And using an Allen key, I'll just fix this in place. Fantastic. As you can see, this end of the beam is rigid, so I can safely assume that this is going to be in a completely fixed position. And my cantilever is this free end, so I'm going to leave it as is. Now you might notice that the beam is already deflecting, and that's because of its own self-weight, which is fine. So what I'm going to do is I'm going to place my deflection gauge right where the beam is resting. Fantastic. Now, also according to your slides, we have calculated the maximum force that I can apply at a distance of 500 millimeters that will generate the maximum allowed moment at the fixed support. We said that this is going to be 1 100 megapascals, and we found out that the maximum force that I can apply to achieve this 100 megapascals was approximately 24 newtons. So we had to select 3 weights that are smaller than 24, and this is what I have. I have 10 newtons, and then I can add 5 newtons, and that will make it 15. Then I can add 5 more newtons, and that's going to make it 20. We're going to take turns applying the loads at this point, and then measuring the deflection right at that free end. And we're going to use the increasing and the decreasing methods, and we'll see which method is going to give us a more accurate reading for the modulus of elasticity. To begin, I have my 10 newtons ready, and I've already set the deflection gauge to 0. What I'm going to do is I'll place the 10 newtons right at the 500 mm mark, and then I can take the reading for the deflection, and that is going to be 10.52. Okay, to increase the load, I'll just place another 5 newtons. So that is going to be 16.26. And then finally, we'll make it 20. And that is going to be 20.95.